Good morning, everyone. I am K. Narsimurthy, working as an assistant professor in the Government First Aid Women's College, Tumkur. Today, I am going to present a video for the course BSc and for the subject Physics. The paper which I am discussing is Semiconductor Devices, Digital Electronics, Laser and Optical Fibers. In that, the topic which I am discussing today is De Morgan's theorem and Boolean algebra. So we are going to learn with a video the very important theorem in the digital electronics, that is De Morgan's theorem, and also we are going to analyze the different combinational logics by applying the Boolean algebra, and we also going to simplify the different logical circuits using this Boolean algebra. Now, firstly, we will go to understand this De Morgan's theorem. This is a very important theorem in the digital electronics. It's a very important theorem. It's just because it can be used to convert one gates into another gates, one OR gates to AND gate. That is possible with the De Morgan's theorem. So we will go one by one. The first De Morgan's theorem. This says that the complement of sum of the variables is equal to the product of the complement of the individual variable, and I have expressed that with a form of an equation. Look at this equation: a plus b whole bar, that is the quantity in the left hand side. A plus b whole bar is the complement of the sum of the variables, and that is equal to the right hand side equation is a bar plus a bar dot b bar. That means the product of complement of individual variable. So left hand side is complement of sum of the variable, and the right hand side is the product of complement of individual variable a and b. So these two are equal according to the first De Morgan's theorem. I'll repeat the statement of the first De Morgan's theorem once again. The complement of sum of the variables is equal to product of the complements of individual variable. That means in the form of equation, it is a plus b whole bar is equal to a bar dot b bar. It means to say, I can explain this equation a little more. First, a and b, which are the two inputs, you first OR this input, means you do the logical addition and then do the complement. Complement in this means do the inversion. NOT gate. NOT gate will do the job of inversion. So first do the OR operation, that means to say logical addition, and then do the inversion. If you do that, and that will be equal to first do the inversion of one input and then do the logical multiplication with the another input which is again inverted. Okay, so that way we analyze the first De Morgan's theorem. So we'll move on to the second De Morgan's theorem, and it says that the complement of product of variables is equal to sum of the complements of the individual variable. This is the equation which represents this De Morgan's second law. A dot b whole bar is equal to a bar plus b bar, exactly converse of the first theorem. So here the left hand side is a dot b whole bar, which is complement of product of variables, and the right hand side is sum of the complements of individual variables. Both are equal according to the De Morgan's second law. Okay, now these De Morgan's first law and second law can also be verified with a truth table. So in the next step, I am going to verify this De Morgan's theorem, showing the equality on both sides of all possible combination values of the variable. And with the help of this truth table, I can do that. So these are the four different combinations of input for two variables. I am taking only two variables, a and as well as b. For the two variables, The 4 different combinations I have written down, and this is left hand side, which is a plus b whole bar, and the last column will be the right hand side. Okay, so it's a little simplification. A is 0, b is 0, a plus b will also be 0. If you do a plus b whole bar, that will be 1. Okay, now if you do a bar, a is 0, a bar will be 1, b is 0, b bar will be 1. If I do a bar dot b bar 1 dot 1, it will be 1. Okay, so look at the third column and look at the sixth column. If both the columns are same, this verifies the De Morgan's theorem with the help of the truth table. So exactly the same way, look at the second combination for 0 and 1. A plus b whole bar is 0 and a bar dot b bar is 0. That's verified. And the third combination 1 and 0, a plus b whole bar is 0 and a bar dot b bar is also 0. And for the fourth combination 1 and 1, a plus b whole bar is 0 and a bar dot b bar is 0 again. So exactly matching the third column, which is left hand side of the equation, and the sixth column, which is right hand side of the equation, are exactly matching according to this truth table. So we verified the De Morgan's theorem, first theorem. We'll move on to the De Morgan's second theorem. In exactly similar way, we verify the De Morgan's second theorem. So first combination is 0, 0. If you do a dot b whole bar, if you do a dot b, it will be 0. If you do whole bar, it will be 1. So individually, if you do the inversion of a and inversion of b, okay, so a bar plus b bar will be 1. So a dot b whole bar is 1 and a bar plus b bar is also 1. Okay, so they are exactly matching. That's the first combination verifies this De Morgan's second law. When you look at the second combination 0 and 1, a dot b whole bar is also 1, a bar plus b bar is also 1. And for third combination, a dot b whole bar is 1 and a bar plus b bar is also 1. And for the last combination, a dot b whole bar is 0 and a bar plus b bar is also 0. This completely verifies the De Morgan's theorem. Yeah. So after the De Morgan's theorem, we'll move on to the laws of Boolean algebra. These laws are the very basic definitions of OR and NOT operation, yielding to the fundamental laws. The definition is yielding to these laws. So if we look one by one, a plus 0 is equal to a. Because if 0 is added to any number, it will be the same number itself. If 0 is added to 1, you will get 1. If 0 is added to 0, you will get 0. Okay. Right. The next identity will be a plus 1 is equal to 1. If anything is added to 1, if either 0 is added to 1 or 1 is added to 1, the ultimate result will be 1. Similarly, a plus a is equal to a. If 0 plus 0, it will be 0. 1 plus 1, it will be 1. So a plus a will be a. So move on to the fourth law of Boolean algebra. A plus a bar is equal to 1. Suppose you assume that a is 0. 0 plus 1, a bar is 1. 0 plus 1 will be 1. Suppose assume a as 1. So 1 plus 0 will be 1. So a plus a bar is equal to 1. Similarly, a dot 0 is equal to 0. So anything, if you do the logical multiplication with 0, it will be 0. So any digit, if you do the logical multiplication with 1, it will be the same number itself. And the one more thing, this is regarding to the AND operations. A dot A will be equal to A. And A dot A bar will be equal to 0. And A double bar, A bar whole bar, if you do the inversion twice, you will get the same number itself. So these are the very basic fundamental laws of Boolean algebra, which are yielded from the definitions of very basic logic gates, OR and NOT gate. So apart from that, we have some general rules. So I'll go one by one. 0 bar is equal to 0. So if you do the inversion of 0, it will be 1. 1 bar is 0. If you do the inversion of 1, it will be 0. Similarly, if you, third one, if a equals to 0, a bar will be equal to 1. If a is equal to 1, a bar will be equal to 0. It's an inversion. Again, the same thing is repeated here. A bar whole bar will be equal to a. We have two laws which is presented here in this slide. One is the commutative law, another one is the absorptive law. These two laws was applied for Boolean algebra. So we'll go what law it is. A plus B is equal to B plus A. It's a commutative law, and that is for the addition. That is for the logical addition. And for logical multiplication, we can write A dot B is equal to B dot A. This is for logical multiplication. And we have an absorptive law for logical multiplication. It's A plus AB is equal to A. And that's for logical addition. And then for logical multiplication, A dot A plus B is equal to A. These two are the absorptive laws, and these laws holds good for the Boolean algebra. And we have two more laws, two more well-known laws, that is associative law and the distributive law, and these laws are also holds good for Boolean algebra. So associative law, if I write for logical addition, it's A plus of B plus C is equal to A plus B of plus C. If I change the order of grouping, and the answer will remain the same. That is the first associative law. This is A plus B within the bracket plus C plus D within the bracket is equal to A plus B plus C plus D. And an associative law for the logical multiplication is A dot of B dot C is equal to A dot B of dot C. Again, if you change the order of multiplication, the answer will remain the same. That applies, that holds good for the Boolean algebra as well. And we move on to the well-known law, another one law, which is distributive law. It is A of B plus C is equal to AB plus AC. And A plus BC is equal to A plus B into A plus C. A plus A bar plus B is equal to A plus B. So these laws are applicable for the Boolean algebra as well. And also with the help of these laws, fundamental laws of Boolean algebra as well as the De Morgan's theorem, we can simplify any logic circuits using these laws. So one of the very simple example I have shown here, it is A plus B C whole bar. If you go on simplifying this with the De Morgan's first law, it's a sum of the complement of the variable is equal to product of the complement of the individual variable. So there is a whole bar here. If I remove the whole bar and put the bar individually, you have to change and R to and. That means you have to change plus symbol to dot symbol. You have to change logical addition to the logical multiplication. Okay. So it is A bar dot B C whole bar. Again, there is another BC whole bar here. Again, you apply De Morgan's second theorem. It's a BC whole bar is equal to B bar plus C bar. Okay. So whole bar can be splitted to the individual variable. Along with that, you have to change the symbol of this. Here, if it is logical multiplication, change it to logical addition. So dot will be changed to plus. So this is the answer, and this is the simplification of the A plus BC whole bar. I have taken a very simple example. Of course, there is a second example which I have taken. The steps have not shown in this. Please, you follow this Boolean algebra and as well as De Morgan's theorem. You will get this answer after simplification. Along with that, there is a very interesting principle here that's called duality principle. Look at these kind of four identities. A plus 0 is equal to A dot 1 is equal to A. Means I am checking for logical addition and for logical multiplication. A plus 1 is A dot 0 is equal to A, 0. A plus A is A and A dot A is A. A plus A bar is 1, A dot A bar is 0. If I look at the keenly about these four identities, in all these above pair of rules, one rule can be obtained from the other by interchanging R and AND operators. So R and operators are interchanged, and by replacing zeros with ones and ones with zeros, this is called duality principle. One rule can be obtained from the other by interchanging the R and AND operators and by replacing zeros with ones and ones with zeros. Look at the first case here. Here the plus means the R operation is replaced by the dot, and that means AND operation, and 0 here is replaced with a 1 here. That identity will hold good. Second case, the R operation plus is replaced by the AND operation dot, and 1 is replaced with the 0. So these kind of identity, these kind of principles are called duality principle. This is called duality principle. And these are the some of the good books which I referred. I'll go fast. Fundamental Principles of Electronics, a good book, and a Tumkur University book which is called Fundamentals of Physics, and a Malvino and Leach, which is a very good old book of the title Digital Principle and Applications with 1991 publications. And we have one more good book which is Sundar College Physics by Sundar Rajan, which is published in 2011. And these are the internet datas. I hope you understand my class very well, and thank you very much.